All right, hello, my name is Patrick North, and that's me on the left, and I'm going to be talking to you today about just, how I personally go about imaging hard targets. So my background is I spent about 10 years as a system engineer doing image analysis, system design development, exploitation algorithm development, and then when I came here to AGI, a lot of the homegrown tools that I had built, I said, it'd be great to be able to have a commercial alternative for a lot of these, to fill in some of the blanks that I was missing, or to generate some pre-data that I would then be able to post-process. And as I mentioned, I'm a sensor guy, so I'm comfortable from 0.28 to 28 microns. I can answer just about any question there. However, I am not a STK power user, and that's one of the reasons why Nova's here, because she covers a lot of the other ground that I don't touch. So, comms, astrodynamics, things like that. We also have Tom Neely here to help us out once we start talking about aviator applications as well. He's our aviator pro, and he's going to help if there's any questions on that. So getting started, we want to just bring up a quick agenda, but then get right into it. So I'm going to talk a little bit about the tools that we're going to use today. So as I mentioned, we're all scientists and engineers. We're working on programs, and we're going to be using different tools to get our job done. And whether it's the pen and paper or Excel, or you're going full-blown SDK and you're going to use that as an integrated package, we're all going to use different tools, and I'm going to show you a lot of the tools that you can use and where you can put in your own data or get intermediate data out to then start processing with your own tools or processes. The three targets that we want to take a look at, we wanted to do space-based imaging, but we wanted to look at things that were on the ground, in space, and then halfway in between in the air. So we tried to pick, pretty innocuous targets. So we said, well, what if we were imaging CubeSats? What are the challenges there? What if we were imaging the ground and we saw, hotspots, or we were trying to detect hotspots and do analysis on those? What if we had a very fast-moving aircraft that was traveling at hypersonic speeds? How hard is that to image from a space-based platform? So we're going to look at those three examples today, and at the end, we're going to talk about, some of the next steps that you can take. More than anything, I want to show you that using a lot of these tools, if they can help you do your work, faster, cheaper, or easier, that's our goal. So we want you to, this is going to be an overview. It's not going to be a detailed training, but we're going to quickly show you what we were able to put together in 2 weeks. This is, just analysis that we did briefly to show off what some of the capabilities are. So this is my 2-second speech on what is SDK. If you aren't familiar with it, Systems Toolkit, you can model Earth, air, land, space, sea. You can put your different objects, whether it's a ship or an aircraft, if it's a ground facility or a spacecraft, whether it's traveling, super fast or stationary, you can model all those different physics-based platforms. Then you can layer in other domains as well. So you can add aircraft or spacecraft with the aviator and astrogator plugins. If you're looking at space radiation or thermodynamics effects, you have the SEAT tool. You can also add in comms, radar, and for me, most importantly, you can also add in that radiometric layer of fidelity with EOIR. Finally, you have both qualitative and quantitative output that's physics-based, and we're going to show off a lot of the outputs that you can generate with this. Hopefully, using all these, we're going to see, primarily, how do we solve these hard targets using thermal infrared from space-based platforms? So the very first scenario that we're going to create is, a satellite looking at other satellites. So we're going to be looking at some CubeSats. And as I mentioned before, as a former system engineer, I need to start with a ConOps. So back when we AGI, we were developing this idea for our commercial space operations center, ComSpoc. We were saying, boy, our sensors are so limited because, a lot of them initially were visible sensors, and as soon as we lost that, sunlight on our targets, we couldn't do any operations any longer. And we said, well, just hypothetically speaking, what good would a thermal sensor do for us? So I'm going to start from scratch with a brand new scenario using SDK, and I'm going to say, well, what could you do thermally in space looking at these other cube satellites? And I want to start from scratch so that you see every step along the way to do this basic piece of analysis. That's important because if you're unfamiliar with SDK or you've seen a lot of demos before, you know that people can sort of gloss over a lot of the hard stuff. And really, we're trying to make this as easy as possible. So here is SDK, Systems Toolkit. You have a 3D window here. You have a 2D map on the right. That's your overhead view. You have your scenario right here, these are the objects that you add to your scenario. You can add a spacecraft, an aircraft, a facility on the ground, things like that. And finally, you have the timeline as well. So if you take a look up here, you have your controls that you can say, all right, well, let's just play the scenario out. Or you can see what scenario you're currently at and jump to a different time in the scenario if you were interested in some particular event happening, things like that. And as I mentioned before, I'm not an astrodynamics guy, so if I go to add a satellite, I just usually say, add me a satellite, and I'll use the orbit wizard. I'll insert a brand new a new platform, space-based platform. I'll use all the defaults, and I'll try and make it so it's visible for the folks online. And by the way, if anything I'm saying isn't clear, or if I skip a detail, please let us know, and we'll try and make that more obvious. So I've now added a satellite to my scenario. If I zoom to this, I see in the 3D window, I can now see my satellite. I can slowly play the scenario out so you can see that everything's synchronized. The 3D window over here, the 2D map view, I can see that I'm traveling where I want to go. So I've got now all my astrodynamic stuff done. But as a sensor guy, well, I want to start looking at my object. So I'm going to take this satellite and I'm going to copy it. I'm going to say, well, I'm going to make this copy. I'll try and stay numerically ordered here. I'll take this satellite and I'm just going to shift it over by a little bit. So I'm going to edit some of those orbital parameters. Now, again, I'm not an astro guy, so I'm just a dummy typing in new numbers in the parameters here. But I'm just going to shift the true anomaly by a degree. And what that's going to do is give me some separation. And I'll change the color of this just so we can tell the difference between our platform is going to be on this blue track and our target's going to be on this red track. So if we shift out a little bit, we can see both our satellites here. And we're going to add a sensor on satellite 1 looking to satellite 2. So pretty darn simple. We'll go here. These are all the different objects that you can add. So you can add, any of these. We're going to add a sensor to our satellite. We're then going to point it. So we're going to say, I want it pointed, targeting our other satellite. And if we now zoom to our first satellite and zoom out, we can see it's perfectly pointed. But this is just a generic sensor. We want an EOIR sensor. So let's go into the properties of that one more time. So here's our sensor. Let's change this to an EOIR sensor. So you have a whole bunch of different types of sensors that you can choose. We're going to choose the best one, EOIR. And I'm going to enter in a few basic system parameters. You can use a lot of the generics if you're interested in. There's spatial, spectral, optical, and radiometric tabs for each of these. So we tried to group these into sensible chunks. There's a number of different ways that you can specify the spatial properties. I know I'm going to have about 40 micron detectors. So I'm just going to change these to the detector pitch or the detector size to 40 microns. I'm going to keep just a small focal plane just for demo purposes. And the default optics are pretty tiny. I'm going to beef these up a little bit because, why not? We're in a simulation. It doesn't cost me anything extra. So I'll make this an F number about 8 and 4 meter focal length. Now if we say, all right, well, let's zoom to our satellite target, and we can see if we back out a little bit, okay, we now have satellite 1 imaging satellite 2, and we're smack dab in the middle of this projected area. And if we then say, well, that's great, I want to now take a picture of it. I've set up all the geometry. So now there's 2 buttons for EOIR. You have the configuration. What is EOIR considering? What are the objects that it's going to consider for ray tracing and radiometry purposes? What's the atmospheric conditions? And the second button is, all right, now that I've done all that, take a picture. So we have 2 satellites. Let's make sure they're both in the EOIR configuration, and then ask just for a nice quick picture. So by default, the default spectral bandpass is visible, and we can see, well, our target's in daylight, and we can see a little dot over here, and that's our satellite. In fact, if we wanted to see some of the radiometric details of it, we can click on it, and we can see, all right, over here, we can see it's satellite 2, we can see the range, about 120 kilometers, we can see the default temperature, the default material, the in-band radiance. So that's all great, but as I mentioned before, this is all during the daytime. What happens if this satellite isn't illuminated? Well, on the timeline down here at the bottom, we can say for satellite 2, we're interested in the lighting conditions. So let's just show what the lighting intervals are for when it's in sunlight. And we can see, well, yeah, we're right in the middle of this sunlit period. Well, what if we jump off of that sunlit period? And just for the heck of it, 1714, we can jump to a time where we know we're not illuminated, and this is right past the edge, and we can see our target's now gone. It's not in daylight any longer. Well, okay, we already knew that was going to happen, though. What if we took this sensor and we copied and pasted it, and instead of just a visible sensor, let's make that thermal. So we'll rename this our thermal sensor, and we'll change some of the properties of it to say, instead of the default spectral bandpass, which is panchromatic, we're going to change this to a long wave thermal infrared sensor. So we'll make it 8 to 12 microns sensitive. So we'll keep a lot of the generic properties. We're not going to go into too much of the specifics yet, but we'll say we're just trying to do a qualitative piece of analysis. We're just doing some general phenomenological studies. Can we see this thermally with a long wave sensor? And the quick answer is, after this renders, yes. In fact, we can see it right there. I'm going to change the color map of this so we can really clearly see it. I'm going to make this a red color map. And if we click around here, again, we can see, again, satellite 2, same properties, but different in-band radiance because we're working at different spectra. And if we jump back in time to when we were visible, so when there was sunlight, we'll actually see it in both sensors. So a visible sensor and a thermal sensor. Now, I asked for permission ahead of time to do this, but if, after this renders, I had a quick question for anybody online that wanted to chat it. So if you want to win a free candy bar, you can respond to this. What we're looking at here, so this is the visible sensor, and this is the thermal sensor, and the objects geometrically are the same size. We have the same spatial properties. We have the same optical properties, but what we did is change the spectra. And the target on the left looks sharper than the target on the right. And if anybody can answer that quickly, there's a reason for that. As I mentioned before, with all of the astrodynamic physics-based properties, with EOIR, there's a lot of physics going into this modeling and simulation as well. And the reason why this is blurrier is because on the visible image on the left, the mean wavelength is about 0.5 microns. Well, in the long wave infrared, the average wavelength is about 10 microns. So that's about 20 times longer of a wavelength. So what we're seeing is the effect of optical diffraction. So again, the same set of optics, same spatial characteristics, we're dealing spectrally with a longer wavelength, and this is exactly what we'd expect. So that's just a nice warm fuzzy to know that, yep, the physics are working, and I'm seeing exactly what I would expect to see. So I'm going to quickly go back and say, so now we've got our, visible versus thermal detection. Really quickly, yeah, we can see it thermally in Umbra, but what if we wanted to go a step further? Well, this is where, for each of these three problems, we're going to model thermal properties differently. And with this one, I said, well, this is great, but just like, the sunlight and the darkness is, good and bad for a thermal sensor, once we're in the darkness, we're going to cool down quite a bit also. And I'm going to change this to the visible sensor, just so I can keep track of myself. How do we come up with the temperatures for objects in space? There's a lot of different ways we can go about doing that, but one of the easy ways is because we're already working in STK, we can change the thermodynamic properties using the SEET, the Space Environment and Effects tool. So what I'm going to do is I'm going to go to the properties of the satellite, and SEET gives you a number of different options here to change. So you can change the radiation properties, the galactic cosmic radiation properties, but we're interested in the thermal properties. And here are the inputs for that. And I'm just going to make this a 50% reflector, 50% emitter, and see what the passive thermodynamics model would give me. Also, we can say, well, because this is a CubeSat, it's going to be operating, it's going to be putting out some amount of power, and that's going to warm up the body a little bit. So we can say, you know what, let's also say, just for the heck of it, that this satellite's dissipating 10 watts of energy. We can hit OK, and we've got all these nice qualitative outputs. We were able to render those images through EOIR, and now what you can do is say, for this satellite, I'd like a report of what that temperature looks like. So you can go here, we can browse this long list of data providers that SDK gives you, and under SEET, we can see that, sure enough, there's a temperature plot that we can generate and say, well, what is the temperature of this object as it's floating around outer space? And from here, we can say, well, here it is in sunlight. It's baking, while it's here. Oh, and also, as a good engineer, I'm not going to use Celsius. I'm going to use Kelvin because that's what my SI units are. So what we can see is here, as we're baking in the sun, we're starting to move farther and farther away from the sun. So our intensity, our projected intensity, our irradiance on the surface is going down a little bit. So we're cooling off. We're about 313 Kelvin here. We drop down to about 293. And then once it goes into shadow, it cools very quickly. And then it bottoms out right about 190 degrees Kelvin. So you can say, all right, well, based on this information, I can now come up with a temperature envelope for my target parameters. I can say, well, it's going to vary between about 180, 190, and about 310 for these target properties. So what I can do is I can say, all right, well, I've got this satellite. I'm going to copy it. I'm going to paste it, and I'm going to set one satellite's temperature to the low end. So this is going to be my cold satellite. So here's the EOIR properties. You can change the shape, the size, the materials, and the temperature. All, shape and size up top. If you have multiple materials, you can set up separate material and thermal characteristics. We'll get into that a little bit later. You can also have time dynamic temperatures. So if we wanted to enter that entire plot, we could do that here with a time temperature profile. Or we can just say, you know what? I'm just going to have a hot and a cold target. So I'm going to set this 180 degrees Kelvin. I'm going to keep all the other material properties the same. Later on, we might want to change it and say, all right, well, I've got a complicated satellite. Maybe it's got solar panels. I'm going to create a complex model. But for now, we're just going to keep it simple. So we've got our cold target here. And we're going to change this to be our hot target. So we're going to change this to 100. We had 180 for the previous one. This will be 310. And for the orbital parameters, I'm just going to move it out of the plane just a little bit so we can see some separation between these two satellites. So here we can see the two different satellites. They're separated just a little bit. I'm going to add it to the EOIR configuration. I'm going to take a picture. So with my thermal sensor, we'll snap a quick picture and see what these two hot and cold targets look like. And just for comparison's sake, we'll add the visible sensor as well. So not too bad. We can easily see both of these targets at both temperatures. So problem solved, right? Well, this is easy enough. I can see my cold satellite, 180 degrees Kelvin down here, and just qualitatively in the image, it's a piece of cake to detect. Well, operationally though, what if it's at various ranges? What if I shifted this satellite that's doing the imaging back a little bit? So just as we shifted forward the true anomaly for the two targets, let's shift this back 0.2 of a degree. And I'm cheating because I already did this, but that's essentially going to increase the range to the targets just enough to make this cold target at the bottom barely visible. So you can see that even though that they're the same temperature, once we start backing off and these are farther and farther away, I can pretty clearly see this target, but this one's really starting to fade out. This is an SNR, summed SNR of about 10, and we can see that, yeah, this is about the limit of detection here. I've only got 1.2 e to the minus 14 watts per centimeter squared, and I think the noise floor is 1 e to the minus 15, so about 10 SNR. If we take a look at the slides, a lot of this I already went through, but we can add both. We can add a thermal sensor, a visible sensor, we can add a mid-wave sensor, we can add 2 or 3 different mid-wave sensors. We can also have multiple bands on each of these sensors too. We now can say, all right, if we were in the early design phases, here's the types of ranges and temperatures that we might be operating at. We can now start to qualitatively generate images. We can start to quantitatively assess what the thresholds are, so we know operationally how can we detect these targets of interest. And then later on, if we were doing a phenomenology study or there's an algorithm bake-off, we can actually generate test data and parametrically change these temperatures and ranges to see how well will these algorithms perform operationally. What if we change the orbits relative to one another? Will we still operate about as well at the detection levels that we were interested in? We had the hot and cold target, and I'd like to just add one more thing too. I never trust any tool for the first time I see it. So what I did is I also measured the irradiances of this, and I said, okay, we had our hot and our cold target, 3.4 e to the minus 13, 1.2 e to the minus 14. And I said, if you wanted to, what I would do anytime I get my hands on a new tool is I verify it with a third party. So I use the Spectral Calculator, which is just a black body calculator online that you can use, and I just really quickly integrated the EOIR band that we use, 8 to 12 microns for 180 and 310 degrees Kelvin. And here were the numbers that it came up for integrated radiance. And I said, well, what's the ratio of this hot to cold radiance? And does that match the measured radiance? And sure enough, we had 28.4 and 28.3. So they're practically spot on. Again, this is a discrete simulator, so it's pretty darn close. It's within a percent. And similarly, I said, well, if we go back and see what was the measured irradiance of the cold target, and if we then said, all right, well, let's take this thermal radiance for the 180 degree Kelvin target, let's put that on a 1 meter radius sphere, let's make it 50% emissive, and let's put it at range 144 kilometers. It's 1.2, and we match about 1.19 watts per centimeter squared. Again, that's E⁻14 for both of these. So I just want to do a quick piece of validation verification to show that, yeah, these are physics-based tools, and yep, they're giving you the right numbers on their outputs. Again, this is just a quick detection analysis, but what might some of the next steps be? Well, here's where, now that we know this can do detections, this is where you're going to want to do those parametric studies for both your targets, what are your temperatures, your sizes, are you a little bit more reflective, a little bit more emissive, and then also your sensor properties. What if we increase the focal length or increase the aperture or decrease both of those or had a more expensive or a less expensive focal plane? How would that change the analysis? You can also say, well, we're just tracking this guy the entire time, but what's our operational scan mode going to be? Are we going to be a stop and stare? Are we going to be, performing some scan operation? How does our operational scan mode match up with our requirements? And, you can do that analysis with this simulation really quickly, really easily. Finally, let's start making it harder. What if we have more stars in the background? Well, with SDK, you can load up a much denser celestial background and start to see, how does that clutter affect your results? And hey, why not see how well we do against an Earth background as well? So that's the quick scenario that I went through. Nova, did you have anything to add to that, or did I hit all the right points walking through this?
Yeah, I think you hit all the right points. I wanted just to throw in there, if you wanted to increase the fidelity of your satellite that's in orbit, or if your satellite's doing station keeping or various maneuvering, the tool you would use in SDK to model that behavior is called Astrogator. And if you guys are interested in modeling satellites, definitely chat in and we can talk to you guys more about that tool.
All right, so this is my first break to take a sip of water and do a quick poll question. Each of these scenarios, I'm going to go through a little bit quicker because you've already seen me set up something with SDK, quickly, and I tried to show off the different panels that are interesting. So for this scenario, I'm going to go through a little bit faster, and then for the third, we're going to go through really fast. But this is now, we've got that same default orbit satellite, and we're now flying over the ground, and we're looking down at wildfires. So I'm going to just load up this scenario. Again, here we start from scratch. For this one, I'll just open one of the existing scenarios that I started building already. So we now have our Exton wildfire scenario. So if you didn't know, the AGI headquarters is in Exton, Pennsylvania. It also happens to be the default place that you create. So in SDK, if you ever add a place, it's going to start probably at our headquarters. And I wanted to use, just sort of an innocuous ground imaging scenario where I said, let's start with wildfires. That's a very relevant topic right now. I said, let's say we had a satellite and operationally, what are we trying to do? Well, detection with a thermal sensor is pretty straightforward, but what's a harder problem? And I thought, well, definitely geolocating where these hot spots are, as well as trying to identify ingress and egress routes. For those, you don't just need sensitivity to perform the detection, you need resolution. And that resolution question is one of the hardest battles between a system designer and an image analyst at the end of the day, because you could do all the quantitative analysis until you show somebody pictures, you're not on the same page. And the inputs for this that I'm going to show you are just a quick reflectance and temperature map. So just as before, we use the seat passive thermal model to give us a temperature profile. Here, what I did is EOIR comes with a global material map and a diurnal thermal model. So you have materials for the entire planet. The problem is they're not very high resolution. And as I mentioned before, this is a resolution problem. So I wanted to start with a real high resolution image. So I started with a Google Earth image that showed me the resolution where I could see individual roadways, rooftops, maybe even the bases of trees or the extent of trees and things like that. And then what I did is I converted this to a reflectance map. I passed it through a thermodynamics model a passive thermodynamics model to see how it would heat up and cool down throughout the day. And then I said, okay, now let's add some hotspots to this data to come up with a temperature map. And that's what you see on the right-hand side. So this is a temperature map that I generated. So I used the left-hand image as a reflectance map, and then I converted that to a temperature map. And what we can do from there is we can then say, all right, here's our scenario. I'm going to try and make this look pretty here on the left. I started with the default satellite once again, and I said, as we're flying overhead, and we're imaging this area, what would that look like? And you know what? I think I probably should have played this video. So here's what our first pass looks like over this target. And let's say we were intentionally looking at this target on the ground because we were worried about hotspots showing up, wildfires. So what would that look like? And once again, I wanted to create both a visible and a thermal output for that. So I said, okay, well, here's what a visible image of that area looks like on this first pass. And we can see these hotspots, if you look at the previous slide, these aren't super hot. They get warm, like these are embers. These aren't, blazing fires that are going out of control, but these are hot spots. And with the visible image, you don't see anything. But with the long wave thermal infrared image, these stick out very clearly. And even if you try and cheat and squint, as good an IA as you might be, you can't see these on the visible side. There's nothing. And even at night, if you looked at these same targets at night, in the visible, you might see a little bit of that hot spot glowing. But in the thermal, it really sticks out. And with the thermal imagery, that's where you get the contextual data too. So if you're doing geolocation and you know the fiduciary point, or you can give a relative geoposition off of something, that's where you really need that thermal infrared image. So I wanted to show, and also this is another good example saying this is the same temperature map for both the visible and the long wave infrared. And you can see the physics are the same. It's applying the same black body equation for both the visible bandpass and the long wave infrared bandpass. So you're getting the same thermal emission physical equations. It's just you're seeing the phenomenology differently as you would expect operationally. So this is great just to see, okay, we're imaging the ground. I can see the hot spots. I can see some resolution. But let's do an actual trade study. And one of the reasons why you want to do trade studies early is because early on in the design life cycle, you have some flexibility with your system parameters. So we're going to trade a few system parameters that maybe early on you have the ability to change. And then later on, once you're getting ready to declare IOC and you're doing your rehearsals and your mission dress rehearsals and you're getting ready to launch, you want to pass through data that's as representative as possible so you can run it through the operational systems to really shake out any of the bugs that you're going to run into day one of operations. So being able to create this high fidelity data that you can then start to do these system design trades or rehearsals with is super important to reduce the time frame from maybe weeks or months of generating this to days, so that you can have these quicker turnaround times and really go through more rehearsals, get more feedback from decision makers, be able to show them operationally what things are going to look like before you actually start bending metal and cutting glass. So traditionally, for trade studies, I'm going to say we're going to vary two parameters: the focal length and the detector size. Those are easy enough to change. We're locked into an aperture of 40 centimeters. So normally, for a resolution problem like this, you might see a plot like this, and it'll say, well, the focal length, if we were to go with a 4 meter versus a 1 meter focal length, here's our IFOV. That's our projected area of a detector, angularly speaking. And we can see that, well, with a longer focal length and smaller detectors, we have a much smaller, much higher resolution sensor system. So that's good. The problem is that, well, we're a physics-based world, so once you start stretching the geometric resolution of your system, you're also going to run into diffraction. So as you stretch to get that 10 microradian resolution, you're also going to be dealing with a higher system Q. If that's essentially the width of the optical diffraction in pixels. So here we've got a blurrier system. So again, you can't get anything for free. By trying to stress this system, we're going to see that, well, if you show this to a decision maker, and I'm a fire chief saying, well, what am I going to do with these numbers? I don't get it. I work on the ground. I send the trucks out to where they need to go. I'm going to put firefighters' lives at risk. I need to know, what I'm going to be seeing with this. And you're telling me this is blue and this is red. I don't know how to compare that. Well, that's why, system engineers, we're going to try and get as representative data into the hands of decision makers as possible early on. And that's what you can do with something like EOIR. So right here, I traded the focal length of 1, 2, and 4 meters and the detector pitch of 40, 80, and 160 microns. And you can see from these images, again, this is the same focal point on the ground, but we can see, all right, well, this resolution I can live with. Maybe it's a little blurrier, but you know what? I can still do my job with it. Or maybe I say, you know what? I can't. I need more context. I need more area in my imagery, and maybe I want to back off that focal length here because, you know, if I'm creating an ingress-egress route and I don't have enough area coverage, maybe I can't do my job. So by being able to provide a qualitative output like this for a system trade study, you can really get to the nuts and bolts of, all right, now as, you know, maybe I'm not a sensor expert, but I can say, if you show me a picture, you know, I give it to my image analyst, can they do their job with this or not? That's the type of analysis that I'd like to be able to get to real quickly with something like SDK and EOIR. So again, you know, some potential next steps. Here's that pass thermally throughout the entire, you know, I just rendered the entire pass, but then we can say, all right, well, this is great, but what if now my bottleneck becomes latency? Well, here's where with SDK, you can start layering in comms and things like that to say, well, what is my turnaround time to downlink some of that data and finally get it to the field operators? Okay, well, maybe this is great for our first orbit, but what if I have different ideas for orbital parameters? Well, that's where you can start to do trade studies to see which orbits will work best for your mission, things like that. You can also say, all right, well, this is all great, but I live in an area with a lot of cloud cover, or I've got drastically different atmospheric parameters. That's where you can start to trade atmospheric properties like, you know, the aerosols, the visibilities, the cloud cover, and things like that to see operationally how's that going to start to affect your day-to-day missions. So that's it for that section. Nova, did I miss anything there? Is there anything you would like to add?
No, I have nothing else to add. I think you covered everything.
All right. So I'll go to the next poll question. I wanted to start with an aircraft-based scenario, and really quickly, all the folks here at AGI are like, you got to make it fly hypersonically. And I was like, I don't know anything about hypersonic speeds, so that's why Tom is here to help answer some of the questions that I don't know. But setting this up again is going to be very straightforward. What I did is I actually started with a scenario that had already been constructed. So this is one of the scenarios that had already been built, and it was a hypersonic glider. And what it shows is this aircraft is flying along, and it's basically skimming, you know, at the cloud layer, and it's going up and down in altitude. And you can see this plot is altitude on the left and Mach on the right. And we can see that, okay, this is traveling pretty fast. What I did is then I took that scenario, I added a basic satellite, and once again, I added one of the default satellites, and I added a sensor to it, and I started tracking this. And I said, well, how good could we see something moving this quickly? So our inputs were the hypersonic aircraft scenario, and for this particular problem, instead of using, well, actually, maybe I can let Tom introduce a little bit of the specifics if you wanted to.
Hi, everybody. I'm Tom. A lot of this stuff is what I've been working on for the last 20 years or so. Pat showed you that airplane that's flying up and down, or we might say it's bouncing off the atmosphere. That's actually an aircraft that's flying a constant angle of attack. And because of that, it boosts up, and because it's flying a constant angle of attack, it will fly a phugoid, what we call a phugoid flight path. And so that's what you see there. And I believe it's about 140,000 feet or so. So it's up there where the air is very thin. So if we can go to the next slide. Aviator out of the box has a variety of performance models, and lately we've built a couple that enable you to fly a full speed range from subsonic into supersonic and all the way out into hypersonic. And these are what I would call first principles types of models. They're not doing computational fluid dynamics. In the case of the aerodynamics, it's using a flat wing, a flat plate model, and so it's representative of some physics, and it has some utility for concepts. And we do get things like the lift and the drag and stuff like that we can calculate from that. So we can generate performance values, and that's what we see on the right here. On the left there, you actually see the power plant model and how its transition zones between the subsonic into, well, in this case, it'd be a turbine on the left, a ramjet in the middle, and then a scramjet out there on the right side. And we're not showing you all the widgets it takes to make those transitions possible, but there's all sorts of dials you can twist in order to make that happen. So when you put that together with the aerodynamics, and I guess the next page is going to have some aerodynamics, or actually, I'm sorry, this next page has the power plant, more power plant, and that shows a specific cruise range on the right side. And on the left side here, you can just sort of see the phugoid flight path. And then if we go to the next slide, that left-hand slide comes off of our aerodynamic model, and it's showing you what we call the stagnation temperature, the total temperature of the wing at that flight condition, using thermodynamic properties in the atmospheric model. And as you can see, or hopefully you can see, and I can't see too well because I have old eyes, but if you get up into the like Mach 9 regions, you start seeing temperatures that are over 3,000 degrees. And so obviously we start having, if you're designing or building an aircraft in that realm, you have to start thinking about how that airplane is going to survive the environment. But obviously, you know, when you see temperatures like that, that means that you're generating a very significant EOIR signature. And I think with that, that's probably a good transition point to come back to Pat.
Yep, absolutely. So with the first example, we used just a real simple primitive for the CubeSats with a few temperature points using that passive thermodynamics model. For the second, we used a temperature map. And for this third one, what we did is we said, let's build up a real basic 3D model of the glider. And let's change the different surfaces to have appropriate temperatures. So we have the top surface, which is going to be the coolest of all the surfaces. Then we're going to have the leading edge that's going to be heating up to this temperature. We're going to be having the exhaust where, we might actually see the exhaust if we're underneath this system. And then we'll have the sides and the underneath, which are going to be somewhere in between that top surface temperature and that leading edge temperature. So if we go to SDK, I loaded up the basic scenario here, and we can see I added a, real simple, I made this an elliptical sun-sync satellite so we'd get more of an overhead path, because if we look at the 2D window here and I play this scenario out a little bit, it's funny, I was joking around with Tom and Nova early and I said, I've never seen an aircraft outrace a satellite before this. But we've got our satellite that's moving south to north, and we've got our hypersonic glider that's just booking up the coastline here. And we can see that the geometry relatively, we're starting almost underneath it, and then we're coming overhead, and towards the end of this flight path, we go all the way to maybe, not a super high angle, but a pretty high angle, maybe like 45 degrees towards the end of this flight path. And if we take a look at the target, as I mentioned before, in EOIR, you can have a variety of, here's the flight path that we saw earlier. And if I go to the EOIR shape properties, what I did is for this guy, I loaded a custom 3D model. That's the model that you can see here on the right. And for that model, we broke it up into different material elements. And for each of these elements, we have the exhaust, the top surface, the leading edge, and the side and bottoms. You can set a different temperature profile. So for example, the leading edge, we can set to 500 degrees Kelvin. And we can change the material properties to be the appropriate ones. I use a lot of simple examples here, but you can fill in the blanks. So for example, even if you had your own lab material spectra for your surfaces, you can load in a custom material if you have it, or you can just use the basics if you don't. So we tried to provide you, at least a good starting point, and if we don't have the inputs that you need, then a lot of times you can load in your own custom inputs. So we've got 4 different temperatures for this guy. And what I did is I said, all right, now I've got these 4 temperatures. Let's see what our signal is for this particular object. I'm going to open up another version of this scenario that Nova was kind enough to create for us, but I'm going to go back to the slides while that's loading up so I can walk through this. And what we see is, again, let's just say, for the heck of it, we wanted to do a test flight, and we wanted an actual sensor to image this. Well, before we even get off the ground, we want to do some simulations to plan that field collect, because a lot of times field collects are expensive. So before you start collecting real data, you can do a lot of the test design and planning with a simulation tool like this, and again, combining with the fidelity of Aviator for your flight path, the fidelity of SDK for all your communications links, your satellite positions, your orbits, and then adding that EOIR radiometric layer of fidelity, you can get a lot of data out of that. And what we were able to figure out from that is, here's the plot of target radiance versus background radiance. And I'll go into this a little bit. What we saw right off the bat is that we had a lot of target signal from this hypersonic glider. And as the scenario goes on, it tapers down, tapers down, tapers down. This background signal in this peach or orange, whatever you're seeing on your screen, that background signal initially, if we go to the scenario, we'll see this is outer space. So we're just seeing, you know, real thin atmosphere here. Then here it goes over certain land cover, and then later on where it gets darker, that Earth background just happens to be water, which just had a lower radiometric signal. And we can see at a certain point we drop below that Earth background signal. And the reason why it's important to use that 3D model with those dynamic target temperatures is because if you use, even if you use a 3D model but you have an effective temperature, that's this green line. And using an effective temperature isn't any good. You know, we're not seeing the effects that you would see with a thermally spatially distributed signal. Again, whether you use a tool like Muses, which can give you the temperature over an entire skin, or if you use a simple model like we did here where we have different surface chunks and average an effective temperature for each of those relevant pieces, you can see the phenomenology is just drastically different. And you really need that to do any of that expensive field test planning that you're going to want to do with a system like this. So if I go back to here, I now have those same graphics up, but what I can do is I can say, well, what's happening at these locations during these different times? And if I show the scenario time on here, I can see, well, you know, here's where I have, you know, pretty good signal, but when I go to the beginning of my scenario, you know, I have the best signal, and the reason for that is we're almost right underneath this glider, and we can actually see the underneath hotter surface areas and the exhaust. But as we play out this scenario and we travel along this plot, we can see here, I'm at a higher and higher elevation angle. I'm seeing less and less of those hot surfaces until the point right towards the end where, wow, you know, I'm just seeing the top coolest portion of this glider. And that's one of the reasons why it drops below the Earth background limit. So you can see even here where I might be seeing some of the hot area with this, you know, real simple thermal model, it's going to say I'm going to lose access much, much earlier as soon as the Earth is in the background. So if we look at the green line, that's our background radiance. We can see here transitioning from space to Earth. Well, you know, if I'm seeing these hot surfaces, I might still have a fighting chance of detecting this thermally. But once I start to get at a higher elevation angle with my sensor and I'm traveling farther and farther out, here I'm starting to lose that. You know, I'm starting to see all top surface for this target, and I'm losing any chance of detecting it relative to the background. So here, it's not an SNR question, it's a contrast question. And that's why you need to be able to model all these different surfaces and all of the backgrounds that you might be dealing with as well. And we can even fly farther out and say, well, I'm seeing the background, this green line change. What's happening there? And we can see, well, it's because we're starting to cover different land types. We're covering different areas on the ground beneath it. And that's why we're seeing different radiance levels. So with that, we can not only validate, you know, or we can plan a actual test flight. We can also validate our model against that, and we can use that to predict future performance capabilities as well. Again, some of the next steps that we could do after this, well, now that we've, you know, got a way to generate test data, we don't need to wait until that test flight. We can actually start passing this to those tracking algorithms or IAs that might be looking at this data to forensically evaluate a scenario and things like that. We can also see how it would look with different combined data sources. What we saw is we get such better signal when we're at that low target elevation angles, when we can see underneath it, how can we combine an enterprise of different satellites that would all have those low grazing angles to give us the best chance at detecting targets like this? How many satellites will we need in different orbits to be able to constantly get that, you know, above this contrast level? And then similarly, once we've got, you know, a lot of that figured out, now it's time to say, well, you know, we're using a nominal atmosphere. What if we throw the kitchen sink at it and say, well, this, if we change the atmospheric properties, there's a few things that modifies. It modifies both the temperatures of our surfaces and it modifies the path radiance that we're going to be seeing optically. So for example, if we're operating in the long wave infrared and we have a subarctic summer versus subarctic winter atmospheric model, you're going to see different path radiances, and those thresholds for detection, this green line, is going to shift. So if we're really concerned in finding those operational limits of detection and tracking capabilities, we're going to want to do a parametric study like that. And that's it for that section. Nova, Tom, anything to add that I might have missed?
I'm tempted to say that one of the things that Aviator will give you is the stagnation and the static temperatures on data providers. So you can use that information to generate dynamic temperature profiles for use within EOIR on your models.
Yep. Yeah. So whether you model with an effective average temperature, if you have a time dynamic thermal profile, or if you have a time dynamic thermal profile for every surface that you're dealing with in your scenario, you can do a lot of that analysis right out of the box, and it's ready to go. So when we talk about next steps, we're hopefully this is a real quick overview. We're right about at 40 minutes, or I'm sorry, 50 minutes. I've gone over by 10 minutes, but hopefully this is a nice snapshot of what's available now. As I mentioned, a lot of this was just done in the last few weeks in my spare time to really show how easy a lot of these tools are to use. There's a lot of capability there. We're not trying to replace the scientists and engineers like yourself, though. We need folks like you who have the problems out there that need solving, and hopefully we've shown you something here today that might make your job a little bit easier. So we know everybody's stretched thin, and if we can give you a force multiplier like STK to help you do more quickly, cheaper, or easier, then we're happy to help you. So I think we've got another set of poll questions, and we're going to wrap it up at the end. Hopefully, if you've been asking questions, Nova's probably been sending you responses on the fly, and we'll spend a few minutes at the end to talk. All right, so to wrap it up, if you didn't see something today that you wanted to see more information on, I have a webpage here, agi.com/EOIR. This is a set of resources where we have high-level overviews where you can see a lot of capabilities that EOIR has for different missions like missile defense, SSA, air-to-air, ground imaging, or scientific applications. This has a lot of the highlights that, just watching something like this, you might see something that piques your interest or answers a question that you have on the tip of your tongue. If you're interested in more of a deep dive into one of these scenarios, we have a number of domain-specific examples. So just like we showed with the CubeSat imaging, if you wanted to see something like that, you could look at the SSA video where we really go into detail and show here's the outputs of SDK and EOIR that you can generate yourself. In fact, we give you the scenario that we use to generate a lot of these outputs. So those might be interesting. If you wanted to get training, we have recorded demos that the SEs have led, and we also have a number of technical documents. So for example, if you wanted to see the validation document for EOIR, this is the 180-page document that goes through every equation. The atmospheric model is in a separate 40-page document here where you can see how we based our atmospheric model on ModTran, and we have a number of validation points. And finally, at the end, we also have a bunch of short capability videos too. So for example, if you want to see, what the output of a true color versus a false color image might look like over a global area, you could take a look at this and see if this is the type of outputs that might help you in what you're doing operationally. We also have lots more training opportunities at agi.com/training. And hopefully, if you haven't bugged Nova yet, you can get an AGI system engineer to get on the line with you. You can get an evaluation copy, and we can start building a scenario together. And then finally, we went through a lot of things today quickly. I hope that if you didn't catch something, you can ask, and maybe this is a reminder. We showed off SDK, EOIR. We talked about SEAT and generating those passive thermodynamics models. There's a lot more that SEAT can do for you. We talked a little about flying someone with an Aviator or setting up an orbit with spacecraft, and you can do a lot more with Astrogator if you're doing maneuvers or launches, things like that. We have Analysis Workbench and Analyzer for adding more, if you wanted more quantitative numbers or to perform an optimization on one of those quantitative outputs, you can do that with those tools. That's about all I've got.
Awesome. Nova, would you like to announce the questions that we have in our Q&A?
Yeah, so throughout the training, thank you all for writing in your questions. There were some of you that I said we could get to at the end of the training class. And so, Pat, I'm going to ask you a couple of questions that came in. One of them was about the temperature profile. Who builds the heat profile? Me and MATLAB. It's the time temperature profile, and I believe they're referring to the CubeSat lesson.
Got it. So with the CubeSats, I'll actually use this as an example. You can generate a thermal profile a number of different ways. So for example, the temperature map, I used Excel for, I'm sorry, I used MATLAB to do the conversion to reflectance, add the passive thermal model to heat it up to the right temperature at the different times of day, and then I added my own hotspot. It uses a Gaussian model and a Poisson distribution to add some heat to different ground regions. For SEAT, you can actually say, this is my satellite. I want a report. So rather than just giving you the plot, you can say, I want it numerically, and you can generate the report numerically, and it'll give you a time temperature profile. Once again, I'm going to change those units as quickly as I can to Kelvin because that's what I'm going to operate in. And you can then either move this to Excel, or if you're a Perl guru, you can convert these to time temperatures to something that you can use with EOIR. And EOIR, you can specify a time profile temperature. And what this looks like, we give you a sample time temperature profile. It's essentially the scenario time in epoch seconds and the degrees Kelvin of that particular surface. So it's real simple to, you can export this to CSV and copy and paste it into a time temperature profile. And if you're doing a parametric study, you could generate the SNR or targeted radiance plots for each of those different time temperature profiles. So you can say, maybe just like with the satellites, you could have a nominal hot and a nominal cold temperature profile and see what the different signal ranges are. So you have an envelope of operations.
Great, thank you. And then there was another one that came in. How do I build my models to detect Blender? And I think related to that is where do I define the surface for radiation and reflectivity?
Okay, good. So I'm glad they mentioned Blender because I love using Blender. When I build models, so another radiometric ray tracing tool that's been out there for a while is DeerSig. And DeerSig used OBJ 3D models. And I said, well, DeerSig's a great tool. I'm going to use OBJs too so that they're cross-compatible. So what we did with EOIR is not only do we say, well, you can read in these OBJ format models, but if you happen to not have any of your own, we provide you a whole bunch of them. And Scott Cross is our 3D modeling expert here at AGI, and he was good enough to generate a few hundred of these for me. So if we take a look at this custom mesh folder, he categorized these as aircraft, ground-based objects, launch vehicles, missiles, sea, space vehicles. And if we go to space, so I'm a satellite, so I better be a space object. Each of these different objects, Scott Cross did a conversion for me. So you come out of the box, EOIR comes with a few hundred different models for each of these different types of scenarios. If you want to use an object that's pre-built for you just to get started day one, you could do that. If you are handy with 3D modeling tools, you can load any of these OBJs up with Blender and then separate out the surfaces. And when you do that, you'll see each surface as a different list item in this material elements. And that's where, just like with the glider, you can set the different surface temperatures and material properties for them. And then finally, if you are not handy with 3D models, but you have a model in mind that you really wish you could get, Scott's pretty darn good about saying, you know what, if we can help you out, we'll get you a 3D model that you can use for your particular piece of analysis or problem. And as soon as Scott's phone starts ringing off the hook, he can yell at me for that.
Thanks, Pat. And then I have two more questions. One of them is, what is the source of the background data and how can I replace it with my own?
That's a good question. So the background data is that diurnal thermal model and global material background map. If instead of using this sensor, let's, just for the heck of it, let's add a second sensor to our satellite and take a picture of the Earth and show you what it looks like. So here's our satellite, and You know, I'll still point it at the target that we're looking at, but I'll make it a much larger field of view. So instead of really zoomed in, let's make this like a nice big field of view. And I'll change this to be a panchromatic band so that nobody who isn't familiar with looking at thermal data will get seasick. If we take a picture, we can see the planet, and EOIR comes with that global material background map, but it's not very high resolution. As you can see, this is the default coarse resolution material map, not very good at all for a lot of applications. And what we can do is we can change that from the default coarse to fine map, and then we'll start to see things. I think it's slightly less than a kilometer square resolution. And here, that's not too bad. We can see here that, you know, we can see the different surfaces. We can see that, you know, this is some good clutter if I'm looking at a broad area. And if we go to details, we can click around and say, all right, I can see the material properties. This is a you know, barren background. Maybe if we travel over this direction, we'll see more grasslands. We'll see deciduous forests, things like that. Each of those materials specifies not just the reflectance emissivity, but also the BRDF properties, the bidirectional reflectance distribution properties. And we can see, like, you know, at the polar caps where we might have some snow and ice, that's going to give you much more of a specular reflection, for example. So we've got a lot of these material properties are built in, and they're going to work great for most broad area scenarios. But if you have your own high resolution reflectance data, like, so for example, when we were looking at Exton earlier with the thermal maps, if I add that default place and stare over there, what I've done is I added a reflectance map and a temperature map and an emissivity map specific for the Exton area. So if I then say I'm going to point sensor 2 over at that place that I just added, so I'm going to stop looking at the glider, and then I start zooming in with this sensor, I'll now be pointed right at Exton, and as I zoom in, that custom reflectance map will start to override that default global material map. So that's how you basically bring in, you do a conversion, you know, from your data, whether you're starting, whatever type of data you're using, you convert that to a reflectance, and then you point to that with geolocated corner points, or if it's orthorectified, you can give it north, south, east, west bounds. I'll start zooming in, and rather than worrying about balancing the system parameters, you can actually, EOIR offers you, I didn't even go through a lot of the sensor properties that are available, but for example, if you don't want to see sensor output, you can cheat and say, I just want the entrance aperture radiance. Give me the radiometric input. Or if you just want a temperature map, for example, if you're using a thermometry tool and you wanted to validate it with ground truth, you can just say, just give me the geometric input, which is a temperature map. And that way, again, if you have your own tools, maybe you don't want to use our sensor model. You want to post-process the data with your own sensor modeling tools. That's fine. You can actually just ask for this radiometric input, its entrance aperture radiance, and then you can post-process that with your own sensor model, for example. Or if you have your own thermal map that you want to override, just like I showed earlier, you know, you don't like the diurnal thermal model that we're using, well, you can override that with a temperature map. Again, just giving those lat, longitude, corner points. So as we're zooming in, you can see here's the default resolution. And if we zoom in even more, you can start to see there's a tiny patch of high resolution ground right around this point. And that's the Exton reflectance map that I'm using to override that global material map. And you can see it's much better. You know, instead of the 1 kilometer resolution, it's like, you know, 1 meter or less GSD. Yep, so there's a perfect example saying, you know, whatever data you have available, we want to be able to work with that. We want you to be able to use the data that you need for your operational missions to see the effects that you would want.
Great. Is that all?
There's another question.
Okay, perfect.
This came in, I believe, after the CubeSat section, so the first main part of the lesson or the webinar. The question is, what is the reason for lower SNR given a larger range? Even with a decaying atmosphere, is there optical attenuation in the vacuum of space, or is the SNR dominated by the pixel pitch? And I believe this is referencing the SNR comparison of the 2 satellites.
So Oh, so the SNR dropped with the longer range, and the idea is that even though the radiance would remain constant, the projected irradiance falls off with the distance squared. So, for example, when we're dealing with sub-pixel targets, normally you'd analytically solve for those with the intensity of your source, and the intensity is going to fall off with, so the irradiance on your focal plane is going to fall off as the intensity divided by the distance squared. So in the examples that we showed much earlier in the slides, when we jumped from, I think it was like 120 to 140 kilometers, the fall off is just that distance squared effect where you're jumping pretty far away relatively. So that's where you're going to start to see that dimmer target fade. It's just, and that's because you're hitting the noise floor. So they're both going down proportionately, but the difference is that one's going below the noise floor and the other's still above it. And one other thing that I wanted to mention briefly too, I showed a lot of the spatial properties. There's not much here. You can specify your spatial properties a few different ways. Your spectral properties, I just showed entering a rectangular bandpass. However, if you have your own system response, you can load in your own system spectral response as well. So for example, if you have a certain shape due to the materials that you use for your focal plane, you can load that in. We also give you a few examples as well. So if you wanted to load in a panchromatic bandpass, or there's a few others that we give you. You can also change the optical properties. I just showed editing the f number, focal length, and the pupil diameter. But depending on the type of program that you are, maybe you have a lab-measured point spread function, or you're using Code V or Oslo or one of the other optical ray tracers, and you have an OTF function. You can load those different optical quality inputs in here, and similarly you can load in your optical transmission spectrally here as well. If you don't have a spectral transmission, you can just use a band effective value. If you don't have it, like I said before, we want to get you started out of the box as quickly as possible, and then the more data you have available, the more inputs that you can start adding to your simulations. And finally, the most complicated slide, or the complicated panel, is probably the radiometric panel, where you can specify a sensor's sensitivity and dynamic range, or if you have those low-level parameters like the quantum efficiency and the dynamic or the read noise, the number of bits that you're quantizing at, things like that, you can start entering in those low-level parameters. You can also specify a lot of the motion parameters down here too, whether you have a long or cross-can smear. If you have jitter, you can load in an RMS or Gaussian jitter model, or if you have a power spectrum for your jitter model, you can use that as well.
Great. I think that's all the time that we have for questions. I see that there are others, but for those that we didn't get to, we will be answering those individually after we sign off, so no worries about that. And make sure to stay up to date on our webinars by visiting agi.com/events. Thank you guys so much for joining us, and thank you to Pat, Tom, and Nova for all of their help. And we'll see you guys next time.